Okay, let's get into this. For years, I mean, whenever we talked about the AI revolution, right,
Yeah.
the picture in everyone's head was, well, it was massive cloud servers, these huge, colossal data centers, just crunching numbers.
Hmm.
But the real widespread deployment of AI today,
Yeah,
it's happening at the other end of the scale.
exactly.
Right on your coffee maker, on the factory floor, inside a drone. We're talking about the rapid shift of AI from central servers out to all these distributed devices. What the industry is calling edge AI.
It's the ultimate push for AI ubiquity. I mean, if AI is going to influence virtually every sector of human activity, it just can't live miles away in a data farm.
No.
It has to be right where the data is collected, where it's processed, and, where it's acted upon.
And that's our mission for this deep dive. We have a fascinating stack of sources that reveal this huge diversity of use cases driving the shift, and, maybe more importantly, the really intensive specialized engineering it takes to run powerful server-grade AI models on hardware that fits in the palm of your hand.
It sounds impossible.
It does, but the engineering is already here.
And what stands out immediately is that the core drivers for pushing AI out to the edge, they aren't, optional luxuries. They're fundamental necessities.
Okay.
We're combining machine learning directly with signal and image processing, and we're satisfying these three huge user demands: immediate data security, guaranteed privacy, and dramatically lower latency.
Right, latency.
The cloud simply can't provide that millisecond reaction time you need in a critical industrial environment. That's why we're building the intelligence locally.
That connection between necessity and location, that feels key. If you're making a critical decision like stopping a machine or rerouting a power grid,
Yeah.
waiting even a few hundred milliseconds for a round trip to a server is it's unacceptable.
It's a non-starter.
So let's start with those core use cases where that local intelligence is an absolute must.
Okay, we can start with something easy to picture: physical security and safety. So imagine a massive perimeter fence or a big public space.
Right.
Instead of streaming every second of video to a central server, which uses just a ton of bandwidth and needs a human to review it, the AI sits right on the camera.
So it's not just passively recording, it's actively deciding what's important.
Precisely. It can detect intruders or find anomalies in crowd movements in real time. If it sees something that requires human intervention, like a package left unattended or a car moving against traffic,
It sends an alert.
instantly, that local processing gives you an instant alert. It turns a dumb camera into an intelligent, autonomous lookout.
The scale of that is impressive.
Yeah.
And the sources highlight this is just as critical in industrial and agricultural sectors, way beyond simple video.
Oh, this is where edge AI really shows its ability to synthesize complex data. I mean, think about a smart factory or a huge agricultural operation.
Okay.
Components are often monitored by dozens of sensors: temperature, vibration, pressure, acoustics, all these different inputs.
Right.
An edge AI model is designed to take all of those and synthesize them into a single, coherent model to identify patterns that humans or traditional systems would just miss.
And if we look at the financial and safety implications here, how does that compare to the old way of doing things? This feels like a core insight for you to take away.
Well, traditionally, engineers relied on what we call deterministic models.
Deterministic.
They set rules based on expected life cycles. This component fails after 10,000 hours, so we replace it then.
But things don't fail on a schedule.
Exactly. Components fail unpredictably. It's like having a rule book but no experienced mechanic on hand.
So the machine learning approach is what, the seasoned mechanic?
It is the seasoned mechanic. Predictive maintenance, which is enabled by edge AI, uses massive amounts of real-world training data about specific temperature spikes, minor vibration shifts, acoustic anomalies, to estimate when and why a specific tool is going to fail.
Ah, so you move from reactive repairs, which means costly downtime,
to informed prevention. And that saves vast amounts of time and money, and it secures both the assets and the workers.
That makes the ROI calculation for edge AI incredibly clear.
Yeah.
And the improvements aren't just in avoiding failures, right? They're in boosting quality during production itself.
Absolutely. The models are trained on what perfect production looks like. If you're managing complex infrastructure, say a city's water supply, the trained model is constantly comparing real-time flow data against that ideal. If production starts to track outside the acceptable tolerance margins, even if it's still technically functional,
The AI flags it.
The AI indicates a problem before the quality degrades enough that you have to scrap a part or make a major repair. It's early detection and proactive mitigation across the board.
Okay, let's pivot a little. Let's move from physical goods to communications and user experience. The AI is also making things run smarter and faster.
Exactly. I mean, in modern telecommunications, AI and ML use continuous training data to optimize channel conditions to make intelligent routing decisions, especially in really high-density environments,
So it's minimizing network congestion.
and improving reliability for everyone on the system.
And then on the human interface side, which is often where productivity is won or lost.
We're seeing massive improvements in accessibility and functionality. Voice and hand gesture control enabled by Edge AI are just essential in hands-free environments.
Like what?
Think surgeons in operating rooms or technicians on a manufacturing line wearing heavy gloves. It enhances safety, ensures hygiene, and just drastically boosts productivity because you don't have to break your concentration to go manipulate a screen.
Right, so we've established that Edge AI is essential: latency, privacy, economic efficiency, across radically different fields, from farming to surgery.
Right.
Which brings us to the core technological challenge: running all these different complex models at the same time on a single tiny chip. It's clear that one size does not fit all.
That's the crux of the engineering puzzle. If you're analyzing voice commands, you're using language model technology. If you're processing sensor data or high-res video for quality control, you're using things like convolutional neural networks or CNNs.
Or high-performance vision transformers.
Exactly. And each one requires a different kind of engine specialization.
And the demand for just raw processing power is accelerating at a terrifying rate. We were already tracking model capacity tripling every year before generative AI came along.
That's right. And the sources show that these transformer-based models, which power so much of this complex AI, they didn't just triple it, they increased that growth to more than tenfold each year.
Wow.
And that sheer computational demand is running headlong into the constraints of these small embedded systems.
So why are those constraints so non-negotiable? Why can't we just use server power and beam the results down?
Because the requirements of embedded and industrial systems are they're diametrically opposed to the cloud model.
How so?
First, data security and privacy are paramount. You can't just send proprietary industrial data or sensitive patient information up to the cloud constantly. It's a non-starter.
Not second.
Second, as we mentioned, the network connection on the ground in a remote agricultural field or a deeply shielded factory is often unreliable, or it's just not there at all.
So the two-part solution is inevitable. We need highly specialized, high-performance embedded processors that are optimized for power efficiency. And we need to ruthlessly adapt those massive server models to run efficiently on these tiny systems.
The emphasis there is definitely on ruthlessly adapting.
Okay, let's get into the engineering magic behind shrinking these immense neural networks. The sources point to specialized architectural advancements that cut the computation costs before the model even hits the chip.
A great example of that is the work done on CNN architectures like ResNet and MobileNet.
Okay.
These were breakthroughs because they maintained high image recognition accuracy while using far, far fewer matrix multiplications than the older models.
Now, how do they do that?
They achieved it by dividing these large, expensive filters, you can think of them as bulky math operations, into smaller, much more manageable two-dimensional convolutions.
So getting the same result via an infinitely cheaper path.
That's a perfect way to put it.
And once that efficient model is on the chip, the next battle is memory. The sources highlight that accessing external memory, the main RAM attached to the processor, is extremely costly, both in energy and time.
It is the single biggest bottleneck. Think of it this way. Your processor has incredibly fast internal caches, like a pit crew working right next to the car.
Right.
External memory is like sending the car down the highway to a distant shop. The physical distance that data has to travel uses power and introduces significant latency.
So how do they keep the data close?
They use a technique called layer fusion. And what this does is it channels successive operations through weight calculations and activation operations across multiple layers before the data ever has to leave the processor's fast internal cache.
So the goal is just to maximize local data processing.
And avoid that costly trip to external memory at all costs.
Now, we often hear about pruning as another optimization technique, sort of cutting away unnecessary connections in the neural network. Does that work well here?
It does reduce the number of operations, yes, but the sources caution that pruning is often counterproductive when you're running on a highly optimized, specialized hardware accelerator,
Ah.
especially one designed for specific matrix multiplications. The complexity you introduce with these random gaps in the network can sometimes make it harder to run efficiently than just running the slightly larger, dense matrix.
So if pruning isn't the magic bullet, we need to focus on what is. And this, I think, brings us to the key technical, the aha moment for edge AI resource management.
It absolutely is, and that moment is quantization.
Quantization.
This is the essential technique that allows for these massive results at dramatically lower energy cost. It achieves this by leveraging specialized SMID, that's single instruction, multiple data arithmetic engines designed for massive parallel vector and matrix calculations.
So what's actually happening when a model is quantized?
Okay, think about storing a high-resolution image, like a massive RAW file from a camera.
Got it.
That's what your model training uses. Wide, high-precision floating point formats, typically 32-bit, that's peak accuracy, but it's also peak storage and compute cost.
Right.
Quantization is the process of converting that data to 8-bit integers or sometimes even smaller widths.
It's like compressing that raw file into a high-quality JPEG. You lose a tiny, almost imperceptible amount of information, but the file size and the processing demand just shrink massively.
Exactly. You get 99% of the result for maybe 1% of the cost. This switch results in a huge decrease in demand for computing resources and, critically, energy.
And because 8-bit operations are so small,
They're so small and simple, you can run many 8-bit engines in parallel for huge performance gains without significantly increasing the chip's energy use or its manufacturing complexity.
that explains the why and the how of model compression. So now let's look at the hardware that makes this parallel 8-bit processing possible. The sources zoom in on Qualcomm's specialized silicon, specifically the Hexagon Neural Processing Unit, or NPU, which is found in both their Snapdragon mobile chips and the Dragonwing industrial system on chips.
And the Hexagon architecture isn't new, it's an evolution. It dates back to 2007. The first version was designed for digital signal processing, or DSP, workloads, using what's called a VLIW, a very long instruction word scalar engine.
Which means the instruction set was designed to do a lot of small, simple things very efficiently all at the same time.
It was inherently parallel and optimized for throughput, even before the big AI boom hit.
So there was some foresight there.
There was. And a key innovation right from the start was the use of SMT, or symmetric multithreading. This parallelism allows the architecture to overcome those huge latency problems from external memory access that we just talked about.
So SMT acts like a high-priority express lane for data, making sure critical information can bypass any traffic jams on that external memory highway.
That's a perfect way to put it. The overarching design philosophy is a unified architecture where developers can use all the resources without hitting constant bottlenecks.
Looking at the current generations of the Hexagon NPU, they've clearly built on that foundation to handle all the diverse needs of edge AI.
They absolutely have. The modern NPU supports parallel vector arithmetic, multidimensional tensors, and crucially, it includes a fully scalar processor that can even run a full Linux operating system independently if it has to.
Without even using the main ARM CPU.
Without relying on the main ARM CPU on the... Yeah. The integration of all these engines, scalar, vector, and tensor all sharing access to a common central memory, it just offers immense flexibility.
And we keep coming back to that shared memory. It seems essential for hitting those ultra-low power targets.
It's the engine of efficiency. They develop features like microtiles, which allow for efficient inference using very, very small units.
Okay, what does that mean in practice?
This is how you run a simple AI model for long periods in a deep, low-power sleep state. Maybe it's just waiting to detect the specific sound of a human voice.
I see.
You can run multiple microtiles at the same time, each one handling a different, simple AI model.
And this common memory architecture enables a complementary optimization technique to layer fusion, right?
Yes, that would be the layer fission. Instead of writing data out to external memory, this common memory architecture allows a deep processing pipeline, often spanning 10 or more layers, to be broken down and processed sequentially without ever leaving the power-efficient environment of the NPU.
Which, again, reduces those external memory writes.
And saves huge amounts of energy and time. It's what makes a device last for hours or days instead of minutes.
So we've got highly optimized hardware and models. The final layer of the challenge, as our sources indicate, is making this incredible, complex technology accessible to the massive number of developers needed to bring edge AI products to market.
That ecosystem commitment is clear. Whether it's Qualcomm's efforts, like their acquisition offer for Edge Impulse, or the release of the Dragonwing socks designed for industrial use, they understand that the best silicon is useless if developers can't quickly deploy code on it.
So what tools are there to help a developer jump that learning curve for rapid deployment?
They developed what's called the AI Hub, which is essentially a library. It provides access to hundreds of optimized model applications that are already tailored for Snapdragon and Dragonwing platforms.
So you don't have to start from scratch.
Exactly. A user can select, download, and test pre-optimized solutions easily, which compresses the development cycle from months down to weeks.
And they've made the hardware itself available for rapid prototyping and scaling up, too.
Absolutely. The sources talk about hardware compute-on modules based on the open SMRC standard. So through agreements with partners like TRIA, developers can get these modules customized quickly
Which shortens time to market.
and increase the scalability for CPU and memory as their applications grow more complex.
And we are talking about incredible performance numbers here.
We are. For instance, the commercially available processors include the QCS5490 and the QCS6490. And for things like high-performance video analytics, the Vision AI Kit, which uses the IQ9075 processor, it's capable of hitting a staggering 100 TOPs.
100 tera operations per second.
A truly revolutionary amount of processing power delivered right there at the edge.
So what does this all mean for you listening? If we step back and look at the full picture, the trend seems locked in. AI is rapidly gaining ground in distributed and embedded applications.
And it's a movement driven not by academic interest, but by the necessity for cost-effective, secure, and exceptionally high-performance models. The availability of these Dragonwing accelerators in modular formats, combined with an accessible library of optimized models and software, it's only going to accelerate this ubiquity.
It's an incredible story of engineering constraint making things smaller and more efficient, actually leading to massive innovation. The technical heart of this efficiency, as we've discussed, is quantization, that trade-off of high-precision floating point numbers for smaller 8-bit integers.
That reduction is responsible for the energy savings and parallel processing capabilities that really define edge AI. It's what makes 100 TOPs possible on a tiny chip.
And this raises an important final question for you to consider. Given that the incredible efficiency of edge AI comes from this data reduction, that shift to the high-quality JPEG version of the model, what kinds of subtle accuracy trade-offs must developers carefully evaluate when choosing between ultra-low power consumption and absolute peak precision for mission-critical, life-dependent edge AI tasks? It's a performance balance that will define the next decade of distributed intelligence.